All right. So in this video, we will go over some questions from intermolecular forces section. Okay. So let's begin with this question over here. So you're given three molecules, and then you are asked what are the types of intermolecular forces exist between pyridosine molecules. So you are referring to this molecule over here. Now, pyridosine is a polar molecule, okay? And then if you have a polar molecule, so for example, you're going to have a dipole moment going into us this way. If you have a polar molecule, you're going to have dispersion and dipole. Okay, you don't have a hydrogen covalently bonded to either nitrogen, oxygen, or fluorine here. Therefore, you're not going to have hydrogen bonding forces, but you have dispersion and dipole forces. Therefore, the correct answer is option C. Okay. Moving on, question 2. Which best describes the molecular polarity of the pyrimidine molecules shown to the right? Okay, so again, when it comes to this molecule, I would say the charges are not symmetrically distributed. For example, nitrogen is more negative than carbon. Therefore, we're going to have a negative charge over here. Okay, and then this charge is going to be not symmetrically distributed. Therefore, you're going to have a polar molecule here. So despite the presence of polar bonds, the overall molecule is non-polar due to symmetry is not correct. There are no polar bonds in this molecule is incorrect. This molecule is overall polar because bond dipoles don't cancel out. That is correct. There are no polar bonds in this molecule is not correct. Okay. All right. Moving on to question 3. Which of the above isomers do you expect to be polar? All right. So we were looking at 3 molecules. Okay, so if you consider pyridosine and pyrimidine, you will have a dipole moment going towards this direction in both cases. But when it comes to pyrosine, right? So you will have one dipole moment here, one over here. They're going to cancel out each other, okay, because of the symmetry. And as a result of that, pyridosine you can expect to be non-polar. Therefore, we would say pyrimidine and not pyrosine. Okay, so pyridosine and pyrimidine only. So it should be it should be option B over here. And not pyridosine only. Pyridosine is the non-polar molecule, and not C because pyridosine is going to be non-polar. And then all of them is incorrect as well. Therefore, the correct answer is option B. Question 4. Determine the bond angles around oxygen labeled X and carbon labeled Y. Okay, so remember we have to fulfill the octet here. So we have only 2 bonds around oxygen now. And then we have to complete the octet, we need to add 2 lone pairs here. And when it comes to carbon, the Y here is an implied carbon atom. We have 3 bonds now. The other bond is fulfilled by a carbon hydrogen bond. Okay. Now around the X atom or the oxygen atom marked X, we have 4 electron domains. Let me write that again. It's going to look something like this. 4 electron domains, 2 lone pairs, and then 2 bonding electron pairs. Therefore, the bonding electron domain geometry is tetrahedral. But if you look at the molecular geometry, it's going to be a bent geometry. And then if you have a perfect tetrahedral, the bond angle should be 109.5 degrees, around 109 degrees. But since we have lone pairs taking up more space, pinching the bond angle of X will be a little bit less than 109 degrees. Okay, so it has to be, it cannot be options B and C because we know X has to be less than 109 degrees. And when it comes to Y, we have we have 3 electron domains around it. Okay, and then these 3 electron domains are bonding electron domains as well. Therefore, I mean, we can say that this is going to be a trigonal planar geometry. If you have a trigonal planar geometry, the bond angle is going to be around 120 degrees. Okay, so the only option that we have Y with 120 degrees is option A. Therefore, the correct answer is option A. Right, moving on to question 5. What is the molecular formula of 2-nitrophenol? So we are referring to this. Okay, so again, we have a line structure here. So in a line structure, we need to replace the ends and bends with carbon. So we have bends. We have 1, 2, 3, 4, 5, 6 carbon atoms. Okay, in all cases, we have 6 carbon atoms. And then the common bonding pattern of carbon should be fulfilled by carbon-hydrogen bonds. So it should be a hydrogen over here, here, and yeah, that should fulfill the common bonding pattern of hydrogen. Therefore, altogether we have 1, 2, 3, 4, 5 hydrogen atoms. Yeah, option A is out, O is out. We are between B and D. And now we need to count the other atoms. We have 1 nitrogen atom. In both cases, we have 1 nitrogen atom. And then we have 1, 2, 3 oxygen atoms. Therefore, the correct answer must be option B. Okay, moving on. Question 6, how many lone pairs do you expect to see in the Lewis structure of levodopa? Let's go back to levodopa over here, which is this big, huge structure over here. Okay, so again, the common bonding pattern of each, not the common bonding pattern, the octet of electrons of each element except for hydrogen should be fulfilled by adding lone pairs, right? So if you think about this, we have oxygen over here, and that oxygen now has 2 bonds. That means 4 electrons. That means we need 4 more electrons. Therefore, we're going to add 2 more lone pairs. Same thing here. We have 2 bonds in this oxygen. Therefore, we have only 4. We need to add 4 more electrons by adding 2 lone pairs. This nitrogen over here has 2 nitrogen-hydrogen bonds and then 1 nitrogen-carbon bond. And then we need to have, that means 6 electrons. We need to add 2 more electrons by adding a lone pair to that nitrogen. Same thing with this oxygen. We need to add 2 lone pairs to fulfill the octet. And same thing here as well. And then we count the number of lone pairs. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 lone pairs in this molecule of levodopa. 9. And therefore, the correct answer is option A. And moving on to question 7. Arrange the following molecules used to produce levodopa from lowest to highest polarizability. So polarizability depends on the number of electrons and the size. Okay, so let's go with the number of electrons. So we have NH3, CO2, and Br2. NH3, nitrogen has 7 electrons, and then hydrogen has 3 electrons. And how do we know this? If you go to periodic table, now let me pull one out if we can. Okay, so if you go to periodic table, nitrogen has the atomic number of 7. That means it has 7 protons. That means it should have 7 electrons as well. Okay, so hydrogen has only one electron. We have 3 of them. Therefore, altogether we have in NH3 you have 10 electrons. In CO2, carbon has 6 electrons and oxygen has 8 electrons each. So you have 2 of them, 16 plus 6, which is 22 electrons. And when it comes to Br2, which is a huge molecule, has 35 electrons in each. And therefore, altogether we have 70 electrons. So based on the number of electrons, we have the highest number of electrons in bromine. Therefore, it must be the most polarizable molecule. And then we have the least number of electrons in NH2. Therefore, NH3, therefore, it must be the least polarizable molecule. Therefore, I would go with option A. That's the correct answer here. Yes, a typo. Option C also has the same same answer. So you could pick either option A or C here. And arrange the following substances from lowest to highest vapor pressure. So we need to go back to the previous page now. Methyl acrylate, 2-nitrophenol, and levodopa. Let's see. So methyl acrylate is the smallest molecule. It has some hydrogen bond. It is a polar molecule, but it is not capable of hydrogen bonding. But both 2-nitrophenol and levodopa is capable of hydrogen bonding, as well as they are huge molecules with more polar sides. Now, I would say the weakest intermolecular forces will be in methyl acrylate. And then between 2-nitrophenol and levodopa, you have many more hydrogen bonding sites in levodopa compared to 2-nitrophenol. Therefore, and it's going to be more polar as well. Yeah, for that reason, I would say that you're going to have the strongest IMFs in levodopa and the weakest in methyl acrylate, and then 2-nitrophenol should be in the middle. Okay, so methyl acrylate will be the weakest intermolecular forces. Which of the following options correctly label the functional groups indicated by X, Y, and Z of levodopa? X is a hydroxyl group, and then NH2 is an amine group, and Z is a carboxyl group. So X is hydroxyl, so that's only B, right? Hydroxyl, Y is amine, and Z is carboxyl. Question 10, how many hydrogen atoms in levodopa are likely to participate in hydrogen bonding forces? So we have 1, we have 2, 3, okay, 4, and 5. 5 hydrogen atoms will likely participate in hydrogen bonding interactions in levodopa. Therefore, the correct answer is option D. What are the electron domain geometry and molecular geometry around nitrogen atom in levodopa? So we are referring to, let me draw that again. Okay, this nitrogen over here, I'm going to redraw that. So we have hydrogen, hydrogen, and a lone pair. Okay, so we have altogether 4 electron domains around it. If we have 4 electron domains, they're going to arrange in a tetrahedral geometry to minimize the repulsions between them. Now, if it's electron domain geometry must be tetrahedral. Okay, so VPG or electron pair geometry, electron domain geometry must be tetrahedral. Therefore, options A and C are out. And then when it comes to the molecular geometry, we're looking at how the bonds are situated here, arranged around the arranged in the space. So they're going to be arranged in a trigonal pyramidal geometry. And then the only answer that depicts that is option B. Therefore, the correct answer is option B. All right, rank the bonds in levodopa from least to most polar, and the polarity of the bond depends on the electronegativity difference. Okay, if you have like say carbon-carbon bond, it's going to have zero electronegativity difference between the 2 atoms because you're subtracting the same value. Therefore, it must be the lowest, least polar bond. Therefore, I'm going to eliminate options C and D where we do not have carbon-carbon bond as the least. And then what we can look at is the other ones. Then we have carbon hydrogen. Okay, so carbon has electronegativity of 2.5, and let me write it over here. Carbon hydrogen, carbon nitrogen, and carbon oxygen. Carbon is 2.5. Okay, and hydrogen is around 2.1, and nitrogen is around 3, and oxygen is around 3.5. And the electronegativity difference, so say delta chi, for carbon hydrogen is around 0.4, and for carbon nitrogen is around 0.5, and for carbon oxygen is around 1.0. You have the greatest electronegativity difference in carbon oxygen bond. Therefore, it should be the most polar, then CN, and then CH bond. Okay, so therefore the correct answer must be option A. So it's up. Moving on. 5-amino true nitrophenol, we don't care about the name. Can be obtained by modifying true nitrophenol. So it's just a modification. Which of the following statements are true about this modification? Okay, so again, the modification is basically you have added this NH2 group. That's the main thing. So you're going to make the molecule more polar, and then you're gonna, that means and also you have added more hydrogen bonding sites because we have nitrogen hydrogen bonds now, and then therefore you're going to increase the overall intermolecular forces. Okay, now let's say the options are: it will increase the melting temperature of the substance. That is absolutely correct. It will decrease the water solubility of the substance. No, I mean you're adding NH2 group here, right? NH2 groups have hydrogen bonding sites, which gives us more opportunities to interact with water, hydrogen bonding and then dipole interactions mainly. Therefore, option the statement 2 is incorrect. And then statement 3, it will decrease the volatility of the substance. Yeah, if we have strong intermolecular forces, it's going to decrease the volatility. Therefore, that is correct as well. Okay, so 1 and 3 are correct. Therefore, the correct answer is option D. Okay, moving on. Solubility of a certain drug in water is depicted in the PEG diagram shown to the right. The statement best describes the solubility of this drug in water. So here, the dissolved state or the mixed state is favored by both potential energy because it has a lower potential energy, and also by the number of configurations because it has a higher number of configurations. Now, this is a situation where this substance is going to always dissolve in water at any temperature. So let's see. The options are: the drug is always soluble in water, which is correct. And the solubility slightly increases when the temperature is increased. No, that is not incorrect. Okay, so the dissolved state or the mixed state has a lower potential energy. Therefore, increasing temperature will slightly decrease the solubility. Okay, not increase the solubility. Therefore, option A is incorrect. Option B, the drug is soluble in water only at low temperatures. That is incorrect. It is always soluble. The drug is soluble in water only at high temperatures. That is incorrect as well. The drug is always soluble in water and the solubility slightly decreases when the temperature is increased. That is correct. Okay, because if we increase the temperature, that is going to favor the state with high potential energy, which is the undissolved state or the unmixed state. Therefore, that will decrease the solubility a little bit. Okay, moving on to question 15. Which of the following diagrams most likely depicts the direction of the net dipole moment of NH3? So not NH3 here, this is a typo. We're talking about this, whatever this molecule down here. Okay, and then if you look at it, the most electronegative atom here is oxygen. Therefore, that will have a partial negative charge. Okay, that area has to be definitely more electronegative. It's going to have a higher density of electrons as a result. Therefore, the arrowhead should be going towards oxygen. Anything that says that the arrowhead is facing any other direction should be incorrect. For example, option A, arrowhead is facing sulfur. Right. Option B looks really good. And then option C is incorrect because it is facing away from oxygen. And then option D is incorrect because it is just showing the carbon-oxygen bond, the polar bond dipole moment, which is not the net dipole moment. So therefore, that is incorrect as well. The correct answer is option B. Last question. CO is more soluble in water than hydrogen. Which statement best describes the relative solubility of CO compared to H2? So you can see that CO is a polar molecule, hydrogen is a non-polar molecule. And if you have a polar molecule, that's going to have more types of interactions with water. So like interacts with like. And as a result of that, you're going to have more ways of arranging with water. When you have CO as compared to hydrogen, therefore it's going to increase the number of configurations compared to hydrogen in water. And also because you're going to have stronger interactions than hydrogen because you have a polar molecule there, you're going to have a lower potential energy in the mixed state compared to the mixed state of hydrogen interacting with water, hydrogen mixed with water. Okay, so if you look at the answers, CO mixed state has a lower potential energy as more polar CO molecules interact strongly with water. That is correct. CO mixed state has more configurations as it can interact with water in more ways. Yeah, that's going to have many more arrangements. So that will increase the number of configurations compared to the hydrogen mixed state with water. And then therefore both A and B are correct, which describes, okay, both A and B describes that. Okay, so neither A and B is incorrect. So I would go with option C over here, which has the correct answer. All right, so those are all the multiple choice questions here. I hope this helped. I'll see you guys in class. Bye, everybody.